we perform some...
Christian, we have a change of program because as I was partly anticipating, unfortunately, Professor Addazzi is not feeling well. And so, I mean, it is not, cannot join us today. But let's say that, I mean, as I had some slides, backup slides, so to say, and so I can deliver the talk, the speech for him. I would kindly ask Catalina then to substitute me.
Absolutely.
Thank you very much, Catalina. And I will start sharing the slide, pretending to be Andrea. So I will give a seminar. Somehow, you know, has been partially covered by Christian, and already Giovanni has done an extensive introduction to the realm of quantum gravity phenomenology and to the use of, let's say, nuclear atomic transitions as laboratory for, let's say, precision quantum gravity. Let's say that I will just slightly remind the testable scenario of quantum gravity. Then I will introduce part of the non-commutative space-times that already Giovanni has been introducing. So I will just focus on a few details. And then, I mean, I'll try to introduce, let's say, the form symmetry and quantum groups in a nutshell, and too many examples, and then what the violation, the limits that we have in the violation of Pauli exclusion principle had to say about non-commutativity of space-time as an arena for quantum gravity. And then, I mean, some comments about, let's say, what nature has to say about that. So let's say that, I mean, it's, of course, quantum gravity is quantum gravity testable. And of course, I mean, it's, we have Giovanni in the audience, who is the initiator, I can say, of this field of quantum gravity phenomenology. And of course, the point is that, yes, we can actually make quantum gravity testable. And there's been a lot of advancement in the last 2 decades or 3 decades about this. So there has been many, let's say, attempts from cosmology and astrophysics to test top-down, but not only bottom-up, also models. There has been also recent claims about the use of quantum gravitational microscope by the group of Rome, gravitational waves, to which I've been reacting with Andrea Addazzi, Nico Junz, and let's say that, I mean, this is also part of another framework in which there's a lot of discussions. So in any way, let's say that probably the best way to try to focus on terrestrial experiments and to look at the limit in which, let's say, the gravitational and quantum effects, let's say, are negligible, but somehow their ratio is not, and introduce, as Giovanni was saying, a new scale. And then, I mean, let me comment on a paradigm, on a shift of paradigm somehow. There's not a shift, but I mean, we have been trying to work more on the coalgebraic sector. So let's say that we have two main roads to test deformation of the symmetry, the space-time symmetries. One is the algebraic sector, which is connected to the, let's say, dispersion relation and to the Hilbert space when quantizing a theory of quantum fields. And the coalgebraic sector, as mathematician would say, and as a physicist would say, the statistics, the issues of statistics, which is related to the Fock space construction when we consider the quantization of fields. And this is intrinsically related also to the emergence of Coulomb momentum space and the form statistics. So in this realm, we have that the spin statistic theorem and non-commutative space-times play an important role. So the spin statistic theorem of Pauli in quantum field theory is based on Lorentz invariance, but we know that, let's say, non-commutative space-time entails the formation of these symmetries. And this is pretty much common when we look, for instance, what's happening in condensed matter, wherever, for instance, we could consider anions, or we could consider any kind of other realization in which, let's say, circuitation of particles among one another introduce a phase or introduce some group elements eventually, which is even more complex as a situation. So we have then, I mean, these effective models of quantum gravity, let's say, may fall inside different classes of universality. And this class of universality can be captured by different samples, by different examples of non-commutative spacetimes. So let's say that the one that I will inspect more properly, let's say more closely here, are the one in which the non-commutativity of the coordinates is of Lie algebra type and is of central type. So let me say that also the symmetry, the Lorentz symmetry, let's say there's a couple of, let's say, at least, I mean, we can divide it in two big families, so to say. So we can have the scenario of a breakdown versus the scenario of deformation. The scenario of breakdown actually is pretty much large because, I mean, it's may introduce, may be due to effects that, let's say, entails violation of the Lorentz symmetry and, let's say, violation of the CVD symmetry through renormalizable operators. But if this happens, we should consider some large amount of fine-tuning, and this usually introduce UV divergences diagram in the standard sector, and then at the end, this affect the requirement of unitarity of the theory. So it's a pretty, let's say, framework that has some weaknesses and is sick in a lot of way. There are also other possible scenarios in which instead of some breakdown of the symmetry, there is a dynamic or spontaneous breakdown of the Lorentz symmetry, which is a better situation. Okay. But still, there may have be generation of normalizable, let's say, power exclusion principle violating operators at scale that are then generated dynamically. Otherwise, we consider indeed the deformation that has been commented, as I say, by Giovanni. And in this case, CPT may not be considered as to be violated, but instead is deformed. So in a let's say in an expansion, in analytical expansion of the deformation parameter, at the zero order, there's no violation. At the first order, there is violation, but then there is restoration of a new symmetry of a new CPT symmetry. There's new way to encode, let's say, the discrete symmetry. So a notable scenario is indeed the one of the theta-Poincare symmetries, and these theta-Poincare symmetries, let's say, that are dual to a non-commutativity of space-time, which is of central type. And in this case, we have that unitarity can still be preserved if the component of this non-commutativity that mix time and space are vanishing. So if the theta 0I component is vanishing. So it has been commented quite longly. And let's say that this scenario actually has been very much interestingly studied in the context of, let's say, string theory, as this is a class of universality for string theory model, since this theta tensor may arise as the Wagner expectation value of the B field antisymmetric in string theory, and flux compactification actually arrives, I mean, entails these solutions, and this is actually the most consistent one that can be actually considered. That is why is so much interesting for this. Seiberg and Witten have been working on that back in the days. So if we want then to, let's say, constrain the power exclusion principle violations, we may consider testing them in all the way. And there is something extremely interesting that the violation of the power exclusion principle may percolate in a way which is democratic through all the sector, or maybe non-democratic in a way which eventually we may call also despotic, in the sense that there may be different way of coupling of the B field with the other matter fields, which is still possible in the sense that, of course, the principle of violence can be the form of violated in the context of the big Riemann scenario of string theory. So let me go now. I mean, it's to the let's say which is the twist element that is used in order to cook, let's say, deformed Lie algebra, but actually this is not even a Lie algebra, this is a Hopf algebra. So this is a quantum groups, so it's non-trivial Hopf algebra. And let's say that the algebraic sector of this deformation, which is the theta Poincare, is actually the same. As you can see, it is just closes the Lorentz algebra. Where you can see that there is actually something non-trivial happening is in the co-algebra. And this hinges toward the fact that because of this, clearly the dispersion relations are supposed and expected to be the same one between energy and momentum for, let's say, particle. While the coalgebra being modified, we can expect that something will happen at the level of the statistics. And indeed, if we want to see what happened at the level of the statistics, we can go switch to the auxiliary, say, representation in the Gordian space, introduce the non-commutativity. So here, the non-commutativity should not be actually taken into account in a way which is, let's say, too serious, so to say. What is really matter here, what is really meaningful, is the deformation of the momentum space. As Giovanni, my master, was advising many times, we should not focus too much in the non-commutativity of the space-time, but it's just auxiliary, but it's important to use it. And through the star product, we can actually introduce a non-commutativity among the space-time coordinates, then expand in Fourier the fields, and then consider product of fields that now will be induced by the star product that have been introduced. And we can now introduce the deformation of the statistics that come from the product rules that are modified for the fields. And this introduces indeed the formed, let's say, relation between the ladder operators that introduced the deformation of the statistics. More in particular, if we use, we take into account twisted fermionic states, we see that there will be an unvanishing overlap probability. For instance, this can be achieved by looking at the twisted single particle wave pocket that we can consider. And now, I mean, it's if we consider the superposition of two of them, we obtain a state that, let's say, will be violating the Pauli principle for non-vanishing values of the energy momentum, the deformation tensor, okay, has been enlightened back in the days by Balachandran, Mangano, and Pinson and other people. And the non-vanishing renormalization now of the Pauli exclusion principle violating state exists, and let's say it vanishing only for a 0-meter set. Let's say that it exists, and a superposition which is not vanishing with any other state which is not Pauli exclusion principle violating. So that is standard in this sense. So let's say that the other case is the one of the k-Poincare symmetries, which is connected to a deformation. So something that we have to keep in mind is that the deformation here for the theta Poincare is something which is linear in a scale, which is quadratic in the energy, or if you want, inverse proportional to the square of the length. And we heuristically assume this to be the Planck energy square, or some also string energy square, which can be, let's say, some order of magnitude even less than the Planck scale, since it is free, somehow can be fixed in a free way. So for the k-Poincare case, which is the one that I enlightened here, the deformation of the algebra is something that allows to have now also a deformation of the energy momentum dispersion relation, but there is even a coalgebraic sector which is deformed. The fact that the coalgebraic sector is deformed does not necessarily imply automatically that there is a deformation of the statistics. Indeed, one has to do an analysis, as we've done before, for the theta Poincare case. In a certain sense, one can always try to move the deformation from the algebra to the coalgebra. Not always is possible, sometimes it is. In this case, as we can see, I mean, as there are deformation, And this deformation of the energy momentum tensor is another channel of observability that indeed is connected, for instance, to the possibility to have superluminal propagation of particles. So there is ambiguity present in the literature. For instance, for k-Poincare, there have been approach, Lacherenkovich-Witten, that we've been developing with Michele Arzano back in the days. But let's say that there are also other attempts by, for instance, the 5D differential 5D differential calculus by Roland Fredel, Kowalski-Glickman, and Novak, Sebastian Novak. Let me say also that there is a paper tracing back to 20 years ago by Giovanni and Michele itself, in which has been considered the, let's say, quantization of theory with k-Poincare symmetries in the momentum space. And in that case, let's say there was a symmetry among exchange of particle that was restored because of the particular interaction vertices that was considered. So the situation is pretty much wide. And so that's why, I mean, it's as Giovanni was correctly saying, it's important to ask nature. So, and the way to ask nature is indeed to take into account this parametrization for the Ladder operators algebra, and to see how the shift with respect to the standard case, which is encoded in this beta square function, or if you want in the delta square function, what can this tell to us? And let's say that in the less trivial case, it's interesting to see that there can be indeed a monochromatic dependence, and this monochromatic dependence is probably the most interesting things that we can go checking. And we can expand then in the power series and see how, let's say, the different order can be constrained from the data that we have on the let's say, Pauli violating transitions, the constraints on the Pauli violating transitions. So here, I mean, it's I go pretty much short on these slides because already Christian has been talked a lot about that. So, I mean, it's I don't also because I mean, it's my time somehow is about to finish also if I had some technical details. But let me say that, I mean, it's of course, there are two types of experiment that we can consider to look at the Pauli exclusion principle violation. So we can look at the search for atoms or nuclei in non-Paulian state, or search for the prompt emission radiation that are containing, let's say, coming with non-Paulian transition of electrons or nucleons. So there are several scenarios here. So, and of course, VIP, DAMA, but not only, Kamiokande and Borexino have been putting very strong, let's say, limits here. So let's say that, I mean, it's among the strongest limits so far that have been considered, but I mean, there is novelty about this for what has been said by Christian. So these slides actually refer to almost 1 year ago. So these are backup slides, so they don't tell the last things that are the one that the Christian was saying. But already, I mean, in this slide, you can see that there are the channels that refers to the photons, to the emission in terms of, say, electrons, and the nucleons, and the limits that is provided on the nucleons on, let's say, the time decay for this transition, which are polyviolating, is actually the tightest one. And if we go combining all this data together, we can see that, so here there is some data from VIP that has been consistently improved recently. Indeed, I mean, this is what Christian was saying. And let's say that, I mean, it's the data from Borexino for the emission, let's say, of neutrons in carbon atom 12 sets a limit of the delta parameters, which is the tightest one, which is 10 to minus 60. And this is enough to, let's say, tells that deformation of the statistic in models like k-Poincare cannot be viable. So if k-Poincare has to be considered, has to be developed in such a way that it does not hold this deformation of the statistics, But as you can see, we are improving now even the data to check to arrive to the level of k equal 2. K here is the order of suppression in the analytic expansion in power of, let's say, energy over the energy scale. And here the energy scale can be pushed up to the Planck scale. And let's say that, as you can see, so far the data is constraint have been coming from Borexino, but there are this novelty that can be considered now. And anyway, we have to consider that there are 3 different channels. And this is extremely important because, as I was saying, we can even have deformation or violation of the Lorentz principle because the theory here allows to have different coupling of the beta fields that after take some vague expectation value that provides this or that value of the theta parameter, for instance, if you're trying to constrain theta Poincare. So let's say that there are new improvement for VIP2, and here, I mean, it's I think that, I mean, it's we can rely on what Christian has been beautifully saying before. Let me say that I want to mention also the fact that Juno will provide also a huge improvement due to the fact that basically there will be a scale of 2 order of magnitude in the liquid scintillator mass, which provide the efficiency mass here. So here, as Giovanni has been saying to me many times back in the days, we have always to consider an amplification, let's say, effect. And the amplification, when we check, for instance, at superluminal effect of the propagation of particle is, for instance, the distance. Distance is providing us the amplification. For this kind of experiments, the amplificator is basically the mass, the effective mass of the experiments. So the number of, let's say, the number of atoms or molecules that can eventually undergo some Pauli exclusion principle violating transition. So, then I mean, it's a simple exercise allows us to see that if Borexino pushed quite close to have, let's say, constraints up to the 3rd order in the analytical expansion in terms of, let's say, energy over scale of energy, Juno may actually arrive to improve this and to improve over beyond, let's say, the 3rd order. So let's say that there is also another part that I want to emphasize here is that so far we have been talking about the algebra and the coalgebraic sector. But if we want to go back to this Cherenkov-Witten approach from which we started with Michele back in the days, in the Cherenkov-Witten approach is indeed the symplectic structure, which is relevant. The symplectic structure is the way we introduce the Heisenberg principle, but the symplectic structure can be deformed as well. And if it is deformed, it encodes also deformation, like goop deformation, okay, that indeed now can percolate also in deformation at the level of the algebra and the coalgebra, so the statistics and of the dispersion relation. The 3 things are very much interconnected. And so let's say that test of Pauli, let's say, exclusion principle violation can also provide information about the generalized uncertainty principle extension. So let me conclude to say that as we have been commenting, we are commenting this session, we can have a new path toward quantum gravity with, let's say, experimental guidance, which is provided now by experiments that have been developed for many reasons for the knowledge of, for instance, neutrino's transition, neutrino's oscillation, Juno, for instance, or dark matter, DAMA, and so on, or neutrino flows, Borexino. So this allows us also to have, since I mean it's the noise must be very well controlled, the background must be very well controlled, allows us to have also information about possible eventual constraints on the eventual violation of the exclusion principle, which traces back to, let's say, quantum gravity at the end. So constraint. So I want then to thank you all, and I think that My time is very well over. So thank you.
Thank you very much. Thank you very much, Antonino.